Alright, hi again everyone. So today's lecture is on Bode Plot 3. This lecture is basically going to be focusing upon what happens when we have a second order system with complex poles. How do we accommodate for this? Indicating that there is going to be some changes in the magnitude and phase plots that we need to observe, and then how do we calculate for the associated parameters that will be associated with these changes in particular. So we saw in the previous lecture, which was Bode Plots 2, is that we were mostly dealing with only real poles. But what happens if the poles now are complex in nature? So if we recall this h of s equation here, which is all the way back from lecture 12, indicating this is the general form for any second order system equation that we will be using. And if we say that we want to find out what is the associated magnitude and phase plots for them, we need to convert from h of s to h of j omega. Now, note that for this case where we observe zeta, we are assuming that zeta lies in between 0 and 1, meaning that our h of s system here is not underdamped or overdamped. We are operating within a set point range for zeta. So, in moving from h of s to h of j omega, it's just a straightforward substitution, where s is equal to j omega. And then we can rewrite this and obtain it into some sort of standard form accordingly. Now in doing this, for us to move to this standard form, what we do is that we make sure that we divide the entire numerator and denominator here by omega naught squared. That's how we get a here by itself, because omega naught squared divided by omega naught squared will be 1. And this 1 component here is given by this point here. The 2j omega zeta omega naught is also given by this component here, and the minus omega squared divided by omega naught squared is given by this component here. Now if we wish to obtain the magnitude of that hj omega equation, it comes like if we try to take the square root of the entire thing where all the components are squared. So a squared here and the square root of a squared will just end up being a. The real component here, if we observe it, is basically 1 minus omega all over omega naught squared, and then we need to square this entirely, and then we add the imaginary component accordingly, so we square that as well, and we take the square root overall. What we observe is that when omega tends towards 0, this entire equation here will end up being that the denominator will end up resolving into 1. So as of such, if we try to take the decibel value for this, we'll just end up getting 20 log of a accordingly. When omega tends towards infinity, on the other hand, what happens here is that, note that this power here being squared and it's going to be squared again, means that it's going to go to a fourth power. A 20 log a component is still going to be there, but now we're going to have a minus 20 log omega divided by omega naught all squared. And the end result would be that we'll end up getting a minus 40 decibel per decade slope for this magnitude plot. The 2 zeta omega and omega naught squared components that we are seeing here will basically have little or no effect compared to this component here, because omega is basically tending towards infinity. So as such, we just basically say 20 log omega on omega naught squared accordingly in order to solve for a magnitude plot. What a resultant magnitude plot equation gives graphically is what we see here in this slide. So if for everything before omega equals omega naught, which is going to be our pole in this case, we're going to have a decibel value here of 20 log of a, which is constant, and everything after it is going to have a minus 40 decibel per decade slope accordingly, as omega tends towards infinity. Now, this is the straight line approximation, but the actual true plot is going to vary differently depending on the value of zeta, because remember zeta is what we refer to as a damping factor. it becomes more apparent when zeta tends towards 0, as we're going to see in the next few slides. So if we want to find out when this graph is going to have a maximum peak, we basically know when this is going to happen when the denominator hits towards a minimum. So if we say, okay, let the denominator equal to d over omega, we also know that if we decide to take the differential of this, we can also find out what was going to be the minimum or maximum accordingly. So if we take the differential of this, we end up getting this resultant equation here. And how we know this hits a minimum is when we solve for the differential being towards 0. And in solving this differential equation here for d omega divided by d omega here equal being 0, we set this part here just to 0, and we solve for omega, we'll end up getting the following equation here mapping omega, omega naught, and zeta accordingly. Please note that this equation holds only true for this particular range of zeta. 0 less than zeta less than 1 under root 2, which is 0.707. What this means is that for this applicable range, the hj omega equation, if we say that the peak here is at omega r, we basically say that that equation we saw in the previous slide is omega r is equal to that equation, and that it holds true only for this valid range of zeta. On typical log scales and magnitude plots, most of the time omega r, mean our resonant frequency, is going to be close to omega naught, which is our natural frequency. So in solving for it equation wise, we tend to use the same value accordingly unless we are given a value of omega r. If we substitute omega equal to omega r into our magnitude equation hg omega, we're going to end up with the resultant magnitude equation as we see here accordingly. And if we transfer this to decibels, it comes like if we just take 20 log of omega r accordingly. So we just say 20 log of the entire equation here. And then we basically start to solve for mr for various values of zeta. Now it's important that you remember this mr equation here, as well as the omega r equation that we saw in the previous slide. So what happens in particular for when we start to change the value of our damping factor here is that we tend to see that when we hit the cutoff frequency, we're going to have a different graphical view of what the magnitude plot is going to look like. So as of such, for less values of zeta, meaning as zeta tends towards 0, we're going to see a more prominent peak accordingly. But as zeta tends towards 0.707, we're going to get our natural curve, which is the actual Bode plot here. And this maps more towards the minus 3 decibel per cutoff point that we observed in previous lectures. So this was basically your h of j omega equation that we had to begin with. We observed the magnitude points for it, basically seeing how the magnitude graph is going to look like. So now let's see what happens if we try to find out what is going to be our phase plot accordingly. Now we can rationalize h of j omega in order to get a more reasonable form, but the explanation I'm going to give you is going to work accordingly respect to it. So this here is our imaginary component, and this here is our real component. If this entire term here on the denominator was on the numerator instead, we basically say tan inverse of the imaginary component divided by the real component in order to find our angle for the equation. But because it's on the denominator now, we basically put a minus sign in front of the tan inverse. So as of such, we will get the resulting equation being here. The minus here indicating that the term was on the denominator that we are accommodating for, tan inverse of the imaginary component divided by the real component. We then observe what happens for when we're at omega tending towards 0, omega tending towards omega naught, and omega tending towards infinity. Now to observe what angles we get in particular. So omega tending towards 0, what happens is that we basically are going to get the resultant graph here being that it's going to be a result of 0 degrees accordingly. Because if we substitute omega here equals 0 into this equation here, we're basically going to see this entire term here, when we find the tan inverse of that, it will end up being 0 degrees regardless. If we substitute omega naught here, this comes like if we have omega naught on the numerator and omega naught here, so that just goes straight down to 1. And now we have omega naught divided by omega naught here, that goes down to 1 as well. And because we divide by 0, it comes like if we find tan inverse of infinity, because we're dividing a real number here by 0, so the end result is going to be infinity. And as such, because there's a negative sign on here, the ending result angle is going to be minus 90 degrees. And then for the final case, when omega tends towards infinity, we're going to see that our end result angle is going to be minus 180 degrees. So what our phase plot ends up looking like is that we observe, for our phase plot, we consider the pole here to be at omega naught. So for everything before omega naught, we basically say we're at a constant phase of 0 degrees. At omega naught, we have a transition from 0 to minus 180 degrees accordingly. The real plot is given by this red line here, but for a straight line approximation, we use a vertical line to represent this transition. And for everything more than omega naught, we basically have a constant phase of minus 180 degrees. Well, what we're going to observe is that when we start changing our damping factor here, in the next slide, this is how the actual magnitude and phase plots change accordingly as well. So as zeta, being our damping factor, tends towards 0, we see in the magnitude plot there's going to be a more prominent peak here accordingly. And as zeta starts approaching towards 0.707, we obtain our usual Bode plot that we've been observing all the time. For our phase plots, what happens here is that as zeta tends towards 0, we get more of a straight line approximation graph that we've been plotting all the time. But as zeta tends towards 0.707, we're going to see that we get that nice smooth curve transition that is the actual phase plot for a stable system. Now, if you're given the following function here as h of s, typically a question comes where it asks for you to find these 4 components regarding the resultant equation. Now we know that from just watching the equation, we can obtain omega naught, because this term here is omega naught squared. Our fall off rate, because we know that it's a second order equation, is going to be minus 40 decibels per decade, as we saw in the previous slides. And then we could calculate for our damping factor and our peak rise and fall. The damping factor is given as the zeta of our system, and we know that this term here was basically some form of omega and zeta, so we can calculate for zeta accordingly. And then we had our peak rise fall resonance being our MR equation that we saw in the previous slides. So what I'd like for you to do is to attempt this problem here and figure out what these 4 components are going to be using the information from the previous slides. What you would see is that if you try to plot this Bode plot accordingly, it ends up looking something like this, where there's going to be a very sharp peak on the magnitude graph, and our phase plot here is going to look much like a straight line approximation. Alright, so in recapping this lecture, what we observed is that when we are doing second order Bode plots, there's a damping factor associated that changes the shape of the Bode plot accordingly. For the magnitude plot we observe as respect to, there's going to be a prominent peak at the cutoff frequency, as we can see here. And that for our phase plots, we see that it's more going to look like a straight line approximation when zeta tends towards 0. As zeta tends towards 0.707 or 1 divided by root 2, we get more of a smooth Bode plot diagram, which is given by that nice smooth curve that we see for the actual Bode plots. We also saw that the resultant equations for MR and omega R can be used in order to solve for these parameters accordingly as well. Finally, what we can also notice is that the damping factor determines the stability of our system. So as zeta tends towards 0, we basically see that our system is basically approaching where it is not stable at all. It is somewhat unstable accordingly. And then when as zeta approaches to 0.707, we approach some form of stability accordingly with the system itself. Alright, so that's it for today's lecture. If you have any questions, please leave comments down below. I'll try to get back to them accordingly as well. Alright, that's it for today.